The underlying concept of multiplication is about proportions and scaling. The simplest cases of multiplication arise from counting the number of boxes in a grid. Example, draw a grid to represent 3 times 5 and compute the product. Notice that we have used a dot for multiplication instead of an x. One of the reasons we do this is that the letter x will often be used as a variable later on in algebra. The product is the result of a multiplication calculation. We will draw all of our grids so that the first number corresponds to the horizontal direction and the second number corresponds to the vertical direction. This is a completely arbitrary choice, and we choose this because this is the same motion that you will eventually use for graphing. One can make arguments that the other way is better, but it really doesn't matter. When counting up the boxes, we will follow the right and up motion and count from the bottom to the top. Again, this is just to emphasize the right and up motion that you will use when graphing. So in the first row there are 3, and then 3 more makes 6, 3 more makes 9, 3 more makes 12, and 3 more makes 15. So there are a total of 15 boxes. This picture explains why people often think of multiplication as repeated addition. In this case, we've added 3 to itself 5 times. However, this idea runs into problems when you start introducing fractions and decimals. What does it mean to add 3 to itself 2/3 times? This is why we stick with the fundamental idea of proportions and scaling. Consider the picture of the product 30 times 4. As you can see, this takes a very long time. Instead of drawing out individual boxes, we can use a picture to represent clusters of 10 boxes at a time. This simplifies the picture and reduces the amount of effort in drawing and counting that needs to be done. Now our picture can be drawn much more efficiently. Example, draw a grid to represent 40 times 5 and compute the product. We will use our clusters of 10 boxes. Then we will count out the total boxes. There's 40 in each row, so 40, 80, 120, 160, 200. 40 times 5 equals 200. Example, draw a grid to represent 8 times 20 and to compute the product. This time, our cluster of 10 boxes will be set up vertically. And now we count up the boxes. Each row now represents 80 boxes. So 80, 160. 8 times 20 is 160. The idea of using clusters of 10 can work in both directions at the same time. This creates a cluster of 100 boxes. Example, draw a grid to represent 30 times 20 and compute the product. Each of these boxes represents 100, so the bottom row represents 300, and another row makes 600. Just as with number line addition and subtraction, the point of having these pictures is to build a conceptual framework to help with future calculations. Students are expected to be able to recall the basic multiplication facts relatively quickly for one-digit multiplication. Example, compute 5 times 7. 5 times 7 is 35. Notice that the presentation is exactly the same as for one-step addition problems. It starts with the original problem, then an equal sign, then the final answer. Example, compute 30 times 9. 30 times 9 is 270. If you're ever unsure about the correct number of zeros to have in the product, just stop and think about the grid. You can see in this picture that we'll be counting in clusters of tens as opposed to ones or hundreds.